Hi, my name is Maya Kapoor, and today I'm going to be demoing for you the system Flurry, which is a fast framework for provenance graph generation. I've been working on this project in the Cyber Resiliency, Security, and Trust Lab at UNC Charlotte with my colleagues Josh Melton and Michael Reidenhauer, and our advisors Thomas Moyer and Siddharth Krishnan. So before I jump into talking about Flurry and its end-to-end pipeline, I wanted to talk some about the background of what you'll see in this demonstration, particularly the software stack. So Flurry itself is an end-to-end pipeline that can take a cyber attack or normal behavior and do some processing and capture and storage and create a provenance graph out of it. This provenance graph can then be adapted to a machine learning application, or a researcher can use it for other learning purposes. And the graph can also be used for causality analysis, for security specialists. The graph can be used for unsupervised learning. There's a multitude of applications for this software. For the components that you'll see of Flurry after this one, the provenance capture and the graph generation, those things can also be used on any virtual machine or server or whatever device you have that's running Linux. They can be imported and downloaded, installed, and also used to capture that execution and transform it into graphs. So we have that separate capability. But Flurry, again, also works as a full pipeline. We can configure Flurry on a VM with this attack simulation software that we also have. And researchers can very simply and very easily, as you'll see in the demo, run attack scenarios, run benign behavior in order to create a clear system execution that they're interested in studying and creating a provenance graph out of. So Flurry comes with some scripts that you can go ahead and run. These are common attacks, things that you would likely see in the wild, things like cross-site scripting, SQL injection on web servers. We also have some network attacks like simulated DDoS and data exfiltration. And then we have some kind of user attacks like brute force password. And for each of these attacks, we kind of divide them into what we imagine the Flurry VM is representing. So things like a web server, or a computer on a network host, or just a regular user machine. So here I have some details about what exactly each of those components runs on in terms of software. So the web server uses XAMPP stack support and runs the damn vulnerable web app. And on that we have some exploitations like cross-site scripting and SQL injection and command line injection. And then we also have a network host configuration where we use hping attacks over the loopback interface to do things like DDoS, data exfiltration, and opening backdoors and doing remote code execution. We also have kind of a user machine configuration where we do a brute force password attack. And for all of these different attack scenarios, we have various benign behavior that we have pre-configured to run as scripts. But as you'll see again in the demonstration, we also offer the ability for you to use this virtual machine and upload your own scripts so that you can run really any kind of behavior you want. You could simulate a particular workflow for a particular machine, or if you have a new attack or a new vulnerability that you're seeing that you want to learn stuff from, then you can script that and upload it and run it and use our provenance capture and graph generation tools and create graphs that you can learn from. So once we have data generated, the system that you'll see that we're using to capture the provenance is CAMFlow in this demonstration. CAMFlow is a practical whole system provenance capture for Linux. So our current version of Flurry, which is version 5 for us, in the beta release we're using CAMFlow support, and we're able to support that on Fedora 34 or Ubuntu 20.04. So when CAMFlow captures provenance, it's a Linux security module which uses hooks to capture provenance from security accesses. Then it conveys that information from the kernel space to user space through a ring buffer, and that user space process picks that up and converts it to a JSON W3C prov format. There are other formats supported, but W3C prov is the one that we're using in Flurry. and that information is piped via an MQT subscriber to Flurry's SQLite database. So Flurry is a subscriber to that pipeline, and Flurry's graph generation software has a component which filters that and is able to parse it. So we have a W3C Prov compliant parser, which works to receive the CAMFlow log input. So any execution that you run that you use the CAMFlow capture mechanism, you'll be able to create a graph out of, and it'll store that in the dynamic storage there. We also offer a parser template with this software. So CAMFlow to Graph is its own library, which can be downloaded from source and used in other projects. The parser template is provided for developers to adapt their own log data. It offers extensibility and adaptation beyond CAMFlow. So again, in this demonstration, we're using CAMFlow, but we also offer the ability to filter just about anything if you can develop it, and then create a provenance graph out of it using our software. So the graph is stored in memory, but it can also be stored to database or some of the various output formats. And I'll be going through all the output formats in the demo, but to give you an idea of some of the capability, so the graph transformer component can work with graph learning libraries. It creates formats that will be supported by those. So we have network X graphs, which can be created, and we can create them with or without features. So we can give you the structural graph, or we can give you a graph with labels. We can also give you a deep graph library graph, again with or without features. The serializer creates graphs in different file outputs. So we can give you a JSON serialized object, which can be easily converted to tensors or NumPy arrays. So we can give you that graph representation. We also have a gpickle serialization. And then for the features themselves, we also offer a one-hot encoded JSON-based object. So we can take a particular feature, for example, the node type, and give you a one-hot encoding of each node in a JSON dictionary, and that can be uploaded into any of your graph learning libraries pretty easily, the way we formatted it. We also have some other supported output that you'll see in the demo. We have a graph statistics file, which gives you a description of the run scenario, node and edge count, types of nodes and edges, and unique node-edge-node combinations. We also offer a drawn summarized image of the graph that we describe as a type graph in our paper, which can be used for a quick visualization of the attack scenario. So jumping into the demos, the first thing that we want to show is a cross-site scripting attack. So in this scenario, we can imagine a user is completing a questionnaire, which is normal behavior on the website, but then we have an XSS reflected style attack where the attacker injects JavaScript into the submission box. So in this demo, I want to showcase how Flurry supports running multiple iterations of the same scenario so that many samples are created. This is for many samples for learning and training. It's also for data verification. You can see that the same thing happens in these scenarios as much as the same thing happens in any system execution. And then we also have reliability testing, and this also enables our attacks to be reproducible over time and by other researchers. And this also shows that Flurry supports the configuration of multiple scripts to be run in succession, so you can kind of modularize your scenario. So in this demo, we'll be showing off the cross-site scripting attack. So I'm going to run the web server module. As you can see, it's very simple to get started. What you're seeing here first is the preloaded scripts. So what's in red here is the attack scripts, and what is in green here is the normal behavior. Now you'll see at the end there are options for custom attack and custom behavior. In another demonstration, I will show what those are and how you can upload your own scripts. But first we're going to look at a scenario with some of the pre-configured scripts. So we're going to run some benign behavior. So it's asking us to select one or more attacks to run in a comma-separated list. This is all you have to do is pick which ones you want. So I'm going to run submit, which is completing a questionnaire, And then I'm also going to run XSS reflected after that. So we have an execution loop, and this is what describes our single graph that's going to be outputted. And now it's asking us how many iterations would you like to make, how many graphs would you like to make. For the sake of the demo, I'm going to make 3. Another configuration option which Flurry supports is to look at particular levels of granularity for provenance capture. So this would be very interesting if you're making your own filters or using a particular level of provenance that you're interested in. For example, if you're interested in targeting web server provenance, you may choose to configure it to only track the HTTP server. If you're interested in database provenance, you're doing SQL injection attacks, then you may be interested in configuring it to focus on the SQL database. Otherwise, if you have some kind of browser level component, maybe you want to capture browser level provenance, you can target just the Chrome browser. Because we're using CAMFlow, we're using whole system, I'm going to run whole system for the demo. Another configuration option that we have is modifying what you'll get for edge and node labels. So the two that we're working with in Flurry version 5, which we hope to expand in future versions, make more configurable. We have what we're calling fine, which is CAMFlow provided node and edge types. So if you go to their website and look at their documentation, they describe what exactly those are. And there's more of them than there are W3C prov model types, which is why we call them fine and coarse. The coarse ones are W3C prov, your agents, entities, and activities, and then also your relation types. So for the demo, I'm going to use coarse edge types, the W3C prov ones, and I'll use fine node types from CAMFlow. So you can combine them as well as use one or the other. So what you're seeing here is we use the Selenium WebDriver to automate the attacks. So first we have to go through the security level with the DVWA app. And it does prompt you for the sudo password. So you can see it's running one of our attack scripts. It's running one of our benign scripts first, and then it's going to run the attack script. So you can see dynamically happening an XSS reflected attack. And since we told it to run it 3 times, it's going to run it again. But before it runs it, it's going to record some of this graph information. So I have the Flurry VM currently configured to save the graph to the database. It's going to draw the graph, the type graph. It makes the gpickle serialization. It makes some JSON files that we'll showcase in a minute. And now it's going to run the attack again. So in the configuration step, we outlined what exactly we wanted our loop to be, that we wanted a benign answer to the questionnaire and then a reflected cross-site scripting attack. And so each graph that we make is going to be that scenario. Alright, so our program has completed running those, and I have it pulled up here so that we can see the output. So our graphs are uniquely indexed from the SQL database. So first of all, let's take a look at the type graph. So you can see this is what the attack looks like summarized. Now if you want an idea of what the attack or the scenario is unsummarized, you can take a look at the stats file. So here we can see this is the statistics for the graph of index 34. The actions we took in this scenario were to submit the questionnaire and do an XSS reflected attack. And the statistics show the number of nodes was 2,241. We have 11 node types, and then we have a breakdown of the nodes per node type. And we have the same thing for edges. We have the number of edges, the number of edge types, and then a breakdown of those edge types. And then most useful for learning, we have the distinct node schemas. So we can see process memory was derived from file, happened 50,312 times. So you can see kind of what is frequent, what is not frequent in some of these examples. And based on these numbers, I hope it becomes clear why this type graph is so useful, because it's an immediate representation of what's happening here in the scenario. So you can see we have some more examples of what these graphs look like. And based on system execution and the way that the graph is drawn, they do look a little different, but if you start comparing the items that you see, they'll be the same nodes, the same edge types just about across the board for these different executions. They just may be in different positions. So for example, while we can run multiple things and make these larger scenarios, we can also make smaller scenarios. So if I were to run this again, I could just run a single submit if I wanted to, and run it one time, whole system provenance. We'll do the same kind of labeling so we can see clearly what the difference might be. And it's going to do the same thing. It's going to open up the damn vulnerable web app, and that way we can clearly visualize the attack and know exactly what's happening and what our graph at the end of the day represented. Alright, so here we have one graph that was the full loop that we ran earlier, that was submit and the attack. And here we have just the submit here. So you can see there's clearly some different nodes, like packet, that are appearing in the attack that aren't appearing in just the benign scenario. So some of that might be evidence in our learning, and of course we use learning algorithms to further study these, but this type graph gives an immediate visualization of that. And overall, this part of the demonstration shows just how you can string attacks together, or do just a single attack, or do multiple iterations or a single iteration with Flurry. It's highly configurable and takes just a few lines on the command line to make it happen. Second attack in Flurry, we want to show the difference between a subtle attack that happens in a low and slow pattern versus a direct attack that is very concentrated. So in the first scenario, we're going to be looking at the user performing a series of normal activities on a network, and then we're going to show an attempt at data exfiltration via writing to an ICMP packet, followed by more normal activity. So you can imagine this is a long-flowing normal system execution. There's a small attack, and there's more normal activity. In ATP style or APT style or advanced persistent threats, you'll often see this kind of attack pattern where you have a lot of small activity or a small amount of attack activity and a large amount of benign activity. So Flurry can simulate that, and Flurry can also simulate just a single attack or just a lot of attacks. Your percentage of benign to attack is very much configurable, which means that Flurry can be useful for a lot of different learning models. If you want to train a supervised learning model that focuses on a specific attack behavior, you can do that. Or you can train an unsupervised learning model to distinguish subgraphs of an attack in a behavior in longer, bigger graph scenarios. Second demonstration, I'm going to be running Flurry on the network host, and we're going to be showing a low and slow attack pattern. So you can see here when we run the network host, the UI looks just about the same, but we've got some different attacks. Currently for a network we support SynFlood, data exfiltration, backdoor, and then a couple different corresponding benign behaviors. And then again, we also support the custom attack and custom behavior, which I'll be showing in the next demo. This particular demonstration, we want to simulate kind of an APT style, where we're doing a lot of normal behavior, and then we have some small injection of attack and some more normal behavior. So I'm just going to add a couple of normal behaviors here: file read, ping, local execution, throw in another file read, and then we're going to add a data exfil. And this data exfil works by trying to copy sensitive information into an ICMP packet. And then we're also going to add a few benign things at the end. So for the sake of the demo, we're only going to do one iteration. And I explained in the previous demo what these different provenance capture levels mean and what the different labeling means. So this particular demonstration doesn't use the Selenium WebDriver. We don't use the WebDriver here. But you can see on the command line it's going to show you what happens. For the file read, it just cats that information out. For the ping, it pings. So it runs pretty quickly. And here you can see as before, we have our output. And you can see kind of a summarization of the entire behavior. And we have our stats file, which tells you this is the actions that were taken, the total number of nodes that we have, and then we have our node and edge breakdown, and of course our node, edge, node schema breakdown. And again, we can also run a more specific attack. So if you're only interested in what specifically the data exfil looks like, you can run just the data exfil. If you want to run one iteration of that just for showing. So you can see it tries to write and transmit the packet. And because we're on loopback, we don't have anywhere for it to go, it doesn't actually transmit anywhere. But we get the system execution behavior, the simulated exfil, which is what matters for the attack. And you can see this is what our graph looks like. And the stats are clearly different. So we have that graph versus this graph. And these might be used for some comparison as well. And you can compare the stats individually. And then you can take these JSON files that describe the graph. You could serialize them or output them out to some learning mechanism. So in this way, Flurry can be adapted to work with an advanced persistent threat scenario, a very targeted supervised learning scenario. And this goes to show that for researchers, we have a lot of flexibility. Flurry is its ability to run custom attack scripts or custom benign scripts. And this is a really important feature for us because it shows that for researchers, we're able to support, first of all, any kind of behavior or simulation of any kind of behavior that you might want. So we can adapt to a lot of different use cases, whether it be a scientific workflow server, a user machine, or some kind of SCADA network. There's a lot of different things that you could simulate, not only attack behavior, but benign behavior that you may want to run. And then for attacks, we can quickly adapt to new attack types. If you can script it, we can run it. So in our scenario that we're going to show in demonstration 3, a new zero-day exploit has been uncovered, and our fictitious researcher Bob needs to quickly train a model to learn its features and detect it. So he scripted this attack and he wants to run it on a sandboxed virtual machine. Well, Flurry can run these custom attacks for normal behavior and use its provenance capture tools to build graphs from it. So this makes Flurry immediately extensible to new attack vectors. Part of the demo, I'm going to show how to run a custom attack script, and you're going to see it's super simple. The hardest part is writing the script to then run. So we're going to run either module will work, the web server or the network host, and I'm going to use a custom attack. So you do need to provide the full path to your custom attack. And we can run Python or shell scripts. So one thing that we do require is that you provide a single word identifier for this custom execution. That's for the stats file so that we can tell you what you ran. So we have our execution loop. How many iterations would you like to make? We can loop these two, so let's make 2 of them. We're going to do whole system provenance again, same labeling for consistency. And you can see this is going to run our brute force attack. And then it's going to output it as it did before. I have the same output settings configured. And so this is using the Hydra password cracker tool to just try 100 password cracks on the Dan Vulnerable web app server. And so you can see here we have this custom script, and we still get, our different type graphs. We get our stats on this custom behavior as shown here. Excellent. And so in addition to running the custom attack by itself, you can also run the custom attack as part of a series. So we might run, for example, we can do a file read, a local execution, then we can do our custom attack, and we can do another file read. So if we have a custom script, we need to provide, again, the full path to it. We might do home, cyber, Flurry scripts. We'll just use the same one. Our single word identifier. We'll just run it once. But you can see it's going to do the behavior we asked it to, then it does our custom script. So this gives you the opportunity, you can put multiple custom attacks, multiple custom behaviors together. And one more example, just to show you can do the custom attack or custom benign multiple times. It doesn't have to be just one. So I could do custom attack, and then provide the full path. And so this is running our custom scripts in succession. And so hopefully this goes to show that Flurry is truly extensible for any research project. Again, if you can script it, we can make a graph out of it. And we can make a graph that has multiple output formats supported. We can support your output into network X, output into a DGL compliant format. We can give you a JSON that you can convert to tensors, to NumPy arrays. We can one-hot encode your features. We can draw you a picture even. So hopefully this demonstration shows that Flurry is highly configurable. It's an end-to-end pipeline that will be useful for machine learning and for graph representation learning on provenance graphs. Much for your time and attention to this demo. If you have further questions about Flurry, you can certainly contact me directly. My email address is provided. If you would like access to Flurry, or you would like to help us with some of our testing, if you have ideas for Flurry, I certainly want to hear it. Please feel free to reach out to me or go to our GitHub repository and download Flurry there and give it a try yourself.